Okay, this is problem 11.65. It's on page 465. Car A is traveling at the constant speed VA. It approaches car B, which is traveling in the same direction at the constant speed of 63 kilometers per hour. The driver of car B notices car A when it is still 50 meters behind him, and then accelerates at the constant rate of 0.8 meters per second squared to avoid being passed or struck by car A. Knowing that the closest that A comes to B is 10 meters, determine the speed VA of car A. Well, let's begin with a sketch of what's going on. Car A, let's do it this way. Car A has some constant velocity VA. Car B, let's draw him on the road, not up above the road. He's not flying. Let's draw it as a truck so that we can differentiate between the two. Car B has an initial velocity of 63 kilometers per hour, but that does not remain constant. Notice it's car B that's accelerating. The initial separation distance is 50 meters. Now, we've got kilometers per hour here, we've got meters here. It's probably best to change to a consistent unit for measuring length. So let's just convert the 50 meters to kilometers. That would be 0.05 kilometers. Now we know that the minimum distance between A and B is 10 meters, but what symbol should we put with that? Well, if we're measuring the position of car A and car B, let's say we just arbitrarily set our x-axis to begin where A begins. If we're measuring the position of these two, then this 10 meters is the distance between them, but both are going to move down the road, and so that's the relative position, because as A moves along, we could talk about the position of A. Let's change colors. Let's talk about the position of A as XA. Later on, of course, the car is going to be at a different location. Let's talk about the position of the truck, or car B. And at some time later, that's going to be over here. They're both moving to the right. But the distance between the two is just the relative position. So if you were to look at the position of A and B as vectors, the difference between those two vectors would be the relative position. So it would be like this. XB less XA is XB with respect to A. So it's just a relative position equation. So what we're saying here is that the relative position is at a minimum of 10 meters, which, by the way, we're going to convert to kilometers, so let's just do that. 0.01 kilometers is the minimum distance between A and B at any point in time. So at that time, what will happen is pretty important. There's something we can extract from this. Let's get rid of the relative position equation. We don't need it. It's just trying to illustrate what this symbol means and what this thing is. At this minimum position, in other words, when the cars are as close together as they're ever going to get, there's something really important that happens there. The velocity of A equals the velocity of B. Now notice the velocity of B is the one that's increasing. So we know this number is going to be more than 63 kilometers per hour. It's the velocity of A that remains constant, and that's what we're trying to find. So just conceptually, what we'd really like to do is to consider how A and B move with respect to time. The curve for A, if I already used the same colored pen for A as I used for the position, the curve for A would just be a straight line, because A continues to accomplish more and more position, but at a constant rate. Okay, so the accumulation of position is constant with respect to time. That just says velocity of A is constant. However, B increases in speed. Now we know that B begins with a lower rate of velocity, or a lower rate of change of position. And so the curve for B is going to be flatter. It's not going to be exactly flat because it's actually moving. So it's going to have a slope, but that slope will be less than the slope of A. However, the slope of B will increase. Now, at the point where the slope of B increases, there's still some separation distance. And basically, the curve for B theoretically looks something like this. So here's the position of B with respect to time. And I've drawn that wrong because I've shown the position of B being less than the position of A. So let me try again. We know that B begins at a position farther along than A, so I shouldn't have put that down where I did. Anyway, we know that the slope is less, but they never intersect. There we go. Now we know that there's some particular time where the distance between the two is at a minimum. So here's the minimum time where the distance between the two is minimized. Okay? And that's what this 10 meters represents. So we'd like to find that particular position or that particular time. And the reason we want to find it is because at that point the slope of B will be equal to the slope of A, and we can figure out the speed excuse me, of A. So what I'm going to do is try to come up with equations for these curves. Now the equation for A is pretty straightforward. The position of A is equal to the initial position of A plus the velocity of A times time. So that's just the equation of a straight line. So the position of A just increases with time. That's what this says. Now if we let the x-axis begin where A begins, where the problem begins, then we can cross that term off. Pardon me. Of course, in doing this, we've set the initial position of B. Excuse me. It must be 50 meters. Because if A is going to begin at 0 meters right here, then B must begin at 50 meters. Now the equation for B, the truck, the equation of this line, in other words, will be a little bit more complicated, but not too bad, because we know that the position of B will be equal to the initial position of B, which is not 0, of course, that's the 50, plus the initial velocity of B times however much time elapses, plus 1/2 the acceleration of B times t squared. Okay, that's just the constant acceleration equation, which we know we can apply because we're told that the acceleration of B is constant. So here's the equation of this line, here's the equation of this line, and we know that at their closest they are 10 meters apart, or 0.01 kilometers apart. Now we'd like to find that particular time, so let's go ahead and look at these two equations, and if you think about it, what you could do is you could take the difference between the two. Now why would I want to take the difference between the two? Well, remember a second ago I had an equation over here that said that the relative position xb with respect to A is equal to the position of B less the position of A. Now I've got two equations here that represent the positions of B and A. So if I simply subtract this equation from this equation, I'll have exactly the relative distance. And why is that important? Well, it's important because I know two data points. I know a data point at the beginning where this value is 50 meters. I know a data point right here where that value is 10 meters. So in fact, what I'm going to do is attach a negative sign to this equation and add them. If you do that, what you'll find is that, let me move this out of the way and put it here, xb with respect to A minimum. You'll find that xb with respect to A is just the initial position of b. Now minus is 0, so I won't write it in, right? So all I'm doing is I'm going to take this equation, write it down, and subtract this one off. Less the velocity of a times time plus the velocity of b initial times time plus 1/2 acceleration of b t squared. Just taking the difference between the two. So I just brought this term down, realized this was a 0, didn't have to write it. I was being inconsistent, and then took this term down, it's got a negative sign attached, and then brought these two down. So that's just the difference between those two. Okay. So let me call this equation 1. Now there's something really important that happens. xb with respect to a at its minimum is when the velocity of a and b are equal to one another. Okay. Now, is there an equation we could use to expand on this just a little bit? Because notice, we don't know the velocity of a, but the velocity of b is something that we could write an equation for. We could use another constant acceleration equation that says that the velocity of b, let's see where do I want to put this. I guess I'll go ahead and get rid of my relative position equation again. I can work down here. The velocity of b is just the initial velocity of b plus the acceleration of b times time. But at the particular time when the minimum distance is observed, okay, before I write this, notice this equation applies at all time, but at the time when the minimum distance occurs, that's when the velocity of a equals the velocity of b. So I could rearrange this equation to solve for the minimum time as the velocity of a less the velocity of b initial divided by the acceleration of b. And so then if I take this particular time and plug it into this equation, then I should have the relative position at that particular time, which is already known. So understanding that all these equations apply to the entire time of motion. So during the entire problem, I'm applying it now to a particular point in time. I'm going to apply it to the time when the cars are the minimum distance apart. So let me call this equation 2, and all I'm really going to do is evaluate equation 1 at equation 2, or at t-min. So basically putting 1 and 2 together, what we find is that at the minimum distance, we're going to have the initial minimum separation, okay, plus the initial velocity of b multiplied by, now here's where I have to plug in t-min. Now I think I'm doing this a little bit out of order. Let's see, which term am I evaluating? So at the minimum time, that term's here. Let me not be confusing. I've got slightly different notes from the way I'm solving it now. Let me be consistent and write that down. And then, let's see, I'm writing a positive term, so I'm taking care of this term first. So actually, let me go out of order from my notes so that I'm consistent with what's on the board. That'll make it easier to understand. So minus VA T, but T is at T-min, so that would be VA less VB initial divided by AB. Excuse me, so that takes care of the first three terms in the equation, plus VB naught, which is just the initial velocity B, which we know that's 63 kilometers per hour, multiplied by, now I need T again, but now it will be the minimum time, and so that would be VA less VB naught divided by acceleration of B. And then finally the last term, plus 1/2 acceleration of B, T squared, but T squared is being evaluated again at the minimum time, so that's V naught less VB naught over AB. Now this looks like a mess, and it is. What I'd like for you to do is to try to solve this. What you'll find is that you've got an equation, and let's see, your unknown is VA. So let me highlight in purple the VA that we're looking for. VA is the unknown in this equation. Notice it appears throughout the equation. You're going to end up with a first order term in VA from here, and a second order term in VA here, with another first order term here. Everything else is a known. For example, XB with respect to A minimum, we know that. That's 0.01 kilometers. The initial position of B, well, from our reference, that's 0.05 kilometers. So that's a known. This is an unknown. VB naught, the initial velocity of B, is a known, 63 kilometers per hour. Acceleration of B is a known. I didn't write it down, but I did read it. The acceleration of B is 0.8 meters per second squared. If you do the conversion to kilometers per hour, you'll find that's 10,368 kilometers per hour squared. So the acceleration of B is a known. Initial velocity of B, we've already seen these. Those are knowns. Acceleration of B, and here I've got an initial velocity, and I haven't made clear what that is. That would be the initial velocity of A. I messed up on my subscript. Pardon me, that's my board support falling. Excuse me, please. Anyway, so the acceleration of B, that's a known. Acceleration of B is known. The velocity of A, there's another copy of our unknown, but that would just be another first order term. And then the velocity of B initial, that's a known. So you can see that everything in this equation is a known except for the velocity of A. Now you're going to get a quadratic equation. You'll have to use the quadratic formula. If you set it up, to help you out, I'm going to show you what your coefficients should be when you get this into standard form. Now standard form would be A VA squared plus B VA plus C equals 0. Your coefficients A, B, and C, if you set A to a 1, you'll find that B should be -2 VB initial, and then C should be 2 times the acceleration of B times the position of B with respect to A minimum minus the initial separation distance between the two. So this is the 10 meters, here's the 50 meters. And then finally plus velocity of B initial squared. Pardon me. So here's your A, B, and C. That's a negative sign there. Try again. There's A, B, and C, and once you plug in the numbers, you'll end up with the coefficients for a quadratic equation. When you finally solve it, what you'll find is that the velocity of A, I'm sorry, I need to move up here, I'm out of space. The velocity of A that you find will be 63 plus or minus 22.8 kilometers per hour. Now, which makes sense? Would we say the velocity of A is more than 63 kilometers per hour, so plus, or less than 63 kilometers per hour? Well, obviously, if A's velocity is less than 63 kilometers per hour, it would never catch B. So we have to choose the positive sign. So the velocity of A comes out to 91.8 kilometers per hour. And there's our speed of car A.